All right, let's do this. So today we're going to continue our discussion of enthalpy. All right, just to remind you all about what we did last week, we introduced these kind of weird chemical equations called formation reactions. We're given a compound formula, we're going to break it up into its elements at standard state, and we're going to balance such that there's a 1 on the product side. All right, and then we said that why these chemical reactions are so important is because we have this table here of these thermodynamic values. So we can find sodium chloride on here somewhere. Cool. And that value given to us in that first column is the delta H of that formation reaction. All right, so this formation reaction here I know has a delta H of that negative 411.2, and the units there were kilojoules per mole. All right, so then we took this was a very specific chemical equation here, right? These formation equations, specifically these synthesis reactions. And then we said, all right, well, what if we want to do what if we want to figure out the delta H for any chemical reaction here? And so what we did was we took our reactants and our products and we broke them up into those formation equations. And then we combined those formation equations together to give us our overall chemical reaction. Okay? And that was kind of this really roundabout process. At the end, we summarized what we did into this equation here, where we can calculate the delta H for any reaction by taking products minus reactants, right? Those delta H values for the products multiplied by their stoichiometric coefficients, minus the delta H values from the reactants multiplied by their stoichiometric coefficients, okay? Cool. So that kind of long pain in the butt process that we laid out at the very beginning here, we didn't call it by its name at the time, but this is what is called Hess's law. Right? Hess's law tells us that we can calculate the delta H of an unknown reaction by combining known reactions. All right, and so that's what we're going to work on here today. Given some known reactions, we're going to combine them together to find the delta H of an unknown reaction. All right, now, if you remember, we kind of laid out these math things that we can do, these math tricks that we can do with these chemical equations. Right? Given some chemical equation where we have its delta H value, if we took that chemical equation and multiplied it by some constant value, we would just do the same thing to its delta H to give us the delta H of that new equation. Likewise, if we have a known reaction, we can flip it around, put our reactants put our products on the reactant side and put our reactants on the product side. And if we do that, the delta H of this new equation, we're just going to flip the sign of our original equation from negative to positive in this case. All right, so we had these math tricks that we laid out as to how we can combine our chemical equations. So first thing we're going to do is kind of just look with variables here. All right, by that I mean we're going to call our target equation our overall chemical reaction. All right, and I want an overall chemical reaction where A gets converted to C. All right, again, we're going to kind of use these variables to simplify things a little bit. And I don't know what the delta H of this reaction is. That's my goal. All right. So what I do know is that I've studied another reaction where A decomposes into 2 of some other compound, B. All right, I know the delta H of this equation here. I've studied it. All right, we're going to call this delta H1 is -6 kilojoules per mole. All right, and I've also studied a second reaction. Okay, this would be like my formation equation here, where half of C gets converted into B. And again, I know this delta H value here. This is positive 3 kilojoules per mole. Okay, I need to combine these two equations here to give me my overall chemical equation. All right, and remember, we got these two tricks that we can do. We can multiply these by any constant value, or we can flip them around depending on what we need here. All right, so if I'm looking at my first reaction, this is the only reaction of my known reactions that have A. And my A is on my reactant side in my overall chemical equation, so I'm not going to need to flip this thing around. All right. If I look at my coefficient for A, it's 1. My coefficient for A is 1 in reaction 1, so I don't need to multiply that by anything. I have this B here, and B does not appear in my overall chemical equation. So that means when I sum these two things up, I'm going to need to cancel out that thing that's missing from my overall chemical equation. All right, let's look at reaction 2. In reaction 2, I have C, but C is on the reactant side of reaction 2 and the product side of my overall reaction. So what am I going to do? I'm going to have to flip it. Okay, so we'll keep reaction 1 as is. Then we're going to take reaction 2, and we're going to flip it. So now I have my product is that 1/2 C, and my reactant is B. And what do I need to do to my delta H for this new reaction that's flipped? I'm going to convert that positive sign into a negative sign. All right, if I sum these two things up, would that give me my overall chemical equation? All right, let's try it out here. We have A plus B gives me 2B plus 1/2 C. I get rid of one of these B's, but I still keep one of them on my product side, so I'm not at my overall chemical equation yet. All right, what else am I going to have to do to that second reaction? Let's look carefully. What is the coefficient of C in my overall chemical equation here? And it's 1/2 over here in my reaction. So I'm going to need to take this whole thing. Not only am I going to flip it, I'm also going to multiply by 2. Take this whole chemical equation here, multiply it by 2. So now I have 2B being converted into C. And when I double that chemical equation, I'm also going to have to take that delta H value and multiply that by 2 as well. All right, so now my new chemical equation here has a delta H of -6 kilojoules per mole. Okay, so now here's my new reaction 1. Actually, it's the same. Here's reaction 2. Whoops, no, it's not. Okay, so now at this point, if I sum up these two chemical equations, I get A plus 2B gives me 2B plus C. And what do I get to do? What can I get rid of? The B's. All right, since I sum them up and I get my overall chemical equation, how do we think we're going to find the delta H of this overall chemical equation? All right, all we did was take this reaction and sum it up with this reaction. And again, we established that enthalpy is a state function here, so it doesn't matter if I convert A to 2B and then 2B into C, I'm starting and I'm ending in the exact same place. So the sum of these two steps, delta H1 and delta H2, is going to give me my overall change in enthalpy. All right, so -6 minus 6, the delta H of this overall reaction is -12 kilojoules per mole. Cool. All right, let's do one more here. I'm going to give you an overall chemical equation. All right, A plus 2C goes to D. We don't know what the delta H of this overall is. That's what we're trying to figure out. All right. What we do know is that C will decompose into A plus 2B. All right, and we also, I guess we know the delta H of this reaction as well is positive 3 kilojoules per mole. Okay, and then we also know that in reaction 2, second reaction that we've studied, 3C will decompose into D plus 2B. All right, when we studied the delta H of that reaction, we got plus 15 kilojoules per mole. All right, given these two chemical equations, I want you to try to combine them in such a way that we get our overall chemical equation, and then tell me the delta H of that overall reaction. All right, so the key here is we got to pay attention to what's going to appear in our overall chemical equation. All right, so what I'm going to do is I'm going to kind of color code to highlight these so we can see where A, C, and D are in that overall chemical equation, where they are in my individual reactions. Okay, A, we got a bunch of C's. Boom. Okay, and we see we got these B's that are going to have to cancel out in the middle here because they don't appear in my overall chemical equation. All right, so we got C, this particular reactant, in both of our chemical equations here. Okay, so it is on the reactant side over here. So it might be tempted to say we want to use reaction 1 with C on the reactant side. All right, but more importantly, there's only one of these reactions that contains A. And A has to be on the reactant side of my overall chemical equation. So I know in reaction 1, I got to flip it. All right, those C's are going to be on my product side, but maybe that will take care of itself when I add my other chemical equation here. But A, there's no other option. I got to put A on the reactant side because it's in the reactant side in my overall chemical equation. And when I flip that chemical equation, what's that going to do to my sign of delta H? Flip it, so now it's going to be -3 kilojoules per mole. Okay. When I look at reaction 2, I have D on my product side and D on my reactant side and C on the D on the product side, D on the product side, and I have C on the reactant side and C on the reactant side. Do I want to flip it or no? No, we're just going to keep it as is. All right, and when I sum these two chemical equations up, I'm going to have A plus 2B plus 3C. All right, but I'm going to get to reduce that C down because I have a C on my product side along with D and 2B. Okay, so when I simplify this thing, it's going to simplify in such a way that I get to cancel those B's out, and I get to cancel out one of those C's, so I'm going to be left with 2. And so indeed now I have my overall chemical equation, A plus 2C, brings me to D. And the delta H of that overall equation is going to be what? The sum of the two, so what's the value of that delta H? Positive 12. All right, one more thing that I can ask you about this equation based on what we did last class is this reaction endothermic or exothermic? All right, and how do we know it's endothermic? Because the sign of that delta H value. All right, positive is endothermic. A negative delta H is an exothermic reaction. All right, cool. So now we're going to do one more, but we're not going to look at like variables. We're going to look at actual chemicals. So there's going to be a little bit more busy going on here. All right, but now we're going to take our overall equation. Got nitrogen dioxide gas plus carbon monoxide. This creates nitrogen monoxide and carbon dioxide. All right, we want to figure out what the delta H of this overall reaction is. Okay, and we've got two reactions that we've studied previously. What we're going to call reaction 1 is when we took 4 moles of nitrogen dioxide and we reacted it to form 2 moles of nitrogen trioxide plus 2 moles of NO. All right, and when we studied this reaction, it gave off a delta H, gave off 314 kilojoules per mole of this reaction. And then we studied a second chemical equation. All right, this is when we took nitrogen dioxide and we reacted it with carbon dioxide. This formed NO3 and carbon monoxide. All right, and when we studied this reaction, we measured the amount of heat that was released. And it was 45 kilojoules, so since it was released, negative 45 kilojoules per mole is the delta H of this reaction. All right, so it's a little bit uglier because we got compounds here. So we got these ugly compound formulas, but the name of the game is the exact same thing that we did last time, where you're going to take these chemical equations and you're going to modify them in such a way that when you add them up, you get your overall chemical equation. All right, and again, we can do that by either multiplying them by some constant value or flipping them, all right, and then we change our delta H accordingly. So everybody take a second, see if you can't figure out how to combine these chemical equations in such a way to produce our overall chemical reaction. That's essentially what you're gonna, wait, the overall equation?
Yeah, the overall equation.
The overall equation's balanced. It has to be balanced to start out with. It's currently balanced. Same number of nitrogens, carbons, and oxygens on both sides.
So then couldn't you just get the delta H from that sheet for each one of those?
Right, but this is a different game we're playing here. You're assuming that something here is missing from that sheet, for example. This is a different way that we have to calculate that same value, same delta H, but this is a new method here, right? So we're assuming for whatever reason we can't use our sheet. All right, so again, I'm going to kind of color code these things just to make it a little bit more clear where these compounds are in these given reactions here. Okay, it makes it a little bit more difficult to see because we have more than one element. We got that state of matter subscript. There's just a little bit more busy stuff for our eyes to be looking at here. So hopefully we kind of see here. Okay. And we'll notice that there's one compound that didn't get colored here, this nitrogen trioxide gas. This is something that's going to have to cancel out when I add these two together because it doesn't appear anywhere in my overall chemical equation. All right, so trying to figure out whether I'm going to need to flip things around or multiply them by some constant value. All right, and importantly, what I'm going to do is I'm going to notice that this first compound, nitrogen dioxide, that is in both of my overall reactions here. It's kind of similar to when we were balancing chemical equations. We said if something's all over the place, kind of save it to the end. Hope it works out at the end. But focusing on that one first is going to be very difficult to figure out how everything should combine together. So I'm going to kind of ignore that NO2 for right now. And I'm going to look and say, all right, well, in this first reaction, my product, nitrogen monoxide, is my product in reaction 1. And that is the only reaction that has that orange compound, that has that nitrogen monoxide. So I know that I'm not going to flip reaction 1 around. That would put it on the wrong side. All right? What I do have, though, is a problem with my coefficient. Nitrogen monoxide in my overall reaction has a coefficient of 1. And in this reaction, it has a coefficient of 2. So what am I going to do to reaction 1? Divide it by 1, or multiply it by 1/2, or divide it by 2, whatever way you want to say. Okay, we're going to take this reaction, we're going to multiply it by some constant value. Okay, if we take reaction 1, we're going to multiply this thing by 1/2. And by that I mean we're going to take the entire chemical equation, multiply it by 1/2. Our delta H value then will be 1/2 of that initial negative 314 kilojoules per mole value. All right, so my new chemical equation here will have all of those coefficients divided by 2. Now we have 2 NO2s decomposing into 1 NO3 and 1 NO. And we're going to take that 314 and divide it by 2, 157 maybe. Not feeling very trusting of my mental math today. Cool. Cool, so now we have our new reaction 1 here and our new delta H value. So now let's go back, let's look at reaction 2. Reaction 2, what am I going to have to do to this one? Flip it, and again, if I look at my nitrogen dioxide, I'm like, well, that's on the reactant side over here, but again, that's everywhere. I'm going to ignore that one. What I'm going to see is that my carbon dioxide needs to be on the product side, and my carbon monoxide needs to be on the reactant side. Those are the only reactions where those two compounds appear. So I need to put those in the right direction. I'm going to take reaction 2, and I'm going to flip it. So now that, whoops, whoa, throwing stuff. Okay, so I'm going to swap my reactants and my products. And what am I going to do to that value of delta H2? It was negative 45. What should it be now? Positive 45. Cool. So now let's take our two reactions and sum them up. Combine all the reactants into one new chemical equation. Those two nitrogen dioxides, the nitrogen trioxide and the carbon monoxide. Then I'm going to combine all my products. Oops. Try to squeeze these together so everything fits. Cool. Okay, now we get to simplify. We better be able to get rid of that nitrogen trioxide because that doesn't appear anywhere in my overall chemical equation. All right, I have two nitrogen dioxides on the reactant side, but only one on the product side. So that means I get to cut this one from the product side and reduce it to just one on my reactant side. All right, and now I have that overall chemical equation, nitrogen dioxide plus carbon monoxide gives me nitrogen monoxide and carbon dioxide. A lot of oxide talk. All right, and then how am I going to get the delta H for this overall reaction? I'm simply going to sum up those two chemical equations I just summed up to get my overall. So 157, negative 157 rather, plus 45 gives me negative 112 kilojoules per mole. All right, so we took our chemical equations and we summed them up to get our overall chemical equation. To get the new value for delta H of that overall reaction, we summed up those two steps. Okay, so to be clear, this is now just the second way that we've discussed to calculate enthalpy. Okay, we talked about Hess's law. That's what we just discussed, as well as using those thermodynamic standards from our constants page. All right, now Joshua asked a very good point. Why the hell are we going to do this long-ass Hess's law sort of thing when I could have just looked up the values on that constants page and summed them up together, right? That was a little bit more simple of a method. We introduced this one first just because it is a little bit more simple of a method, okay? But importantly, the using of those thermodynamic standards depends 100% on Hess's law. If Hess's law wasn't true, we couldn't take those formation equations and combine them together in that simple equation that we used to get our delta H value, right? So even when we're using those thermodynamic standards, really we're still using Hess's law. It's just convenient that they've tabulated those thermodynamic standards for those formation reactions, those specific types of reactions. Those can always be combined to give you any chemical reaction, okay? And so the bottom line is, like, when can we not use our thermodynamic standards? Well, if one of the compounds in your reaction isn't on that table because a scientist hasn't studied it yet, this is another way that you could get at that value, using other reactions that you had studied before. What's up?
How did you know to multiply reaction 1 by half?
Because my coefficients in my reaction 1 for this nitrogen monoxide was too high. right? This is the only, out of reaction 1 and 2, there's only one reaction that has nitrogen monoxide, that orange compound. So I gotta make it match what's in my overall chemical equation. Okay, we talked about thermodynamic standards for what we're gonna call general reactions. All right, now we're gonna throw in a little bit of a complication here for dealing with aqueous reactions. We're still going to use those thermodynamic standards. We're still going to go for our products minus reactants business. All right, we just got another sort of complication to throw at things here. So, out of these aqueous reactions, these solution reactions, there are a few different ones that we studied, and we studied them pretty in-depthly in terms of being able to predict these reactions, right? So one of these were these simple single replacement reactions. Y'all thought this stuff was going away. Coming back strong, all right? Where we had a metal plus an aqueous solution would give us a metal plus an aqueous solution. All right, so for example, if we take zinc and we mix it in with a solution of copper 2 chloride. Everybody take a second and predict the products of this single replacement reaction. All right, so in my reaction, my zinc and my copper, they swap places. So now copper is all by itself in its standard state where it's a solid. And the zinc is in a compound with those chloride ions. Right, zinc, because it's one of those type 1 metals that we just got to know, has a charge of +2. So when I do my formula here, it's going to be ZnCl2. Right, so those single replacement reactions, we're going to swap those two metals. Now we have copper all by itself and zinc with those chlorides. Cool. So if you tried to go to that constants page and look up everything in this chemical equation here, you wouldn't find it. All right. In particular, you wouldn't find those aqueous compounds. What we need to do here is first break this up into what we call the net ionic equation. All right, let's do this reactant side together here. For my net ionic equation, if I come across something in my balanced chemical equation that has any subscript other than AQ, I'm going to copy and paste it down below, not changing a thing. Right? Zinc has that solid. I'm just going to copy paste. I'm not going to put charges. I'm not going to alter anything. When I get to my aqueous compound, though, this is when we break these up into cation and anion. So my copper chloride here, copper 2 chloride here, has that AQ. So I'm going to break this up into a copper 2 ion and 2 chloride ions. All right, so given that, everybody take a second, see if you can't break up your product side as well, right? What is the net ionic, well, really just the ionic, and then we'll go through and cross stuff out to get the net ionic. All right, but yeah, see if you can't fill out the product side over here. right? This would be copper. I'm just going to copy and paste that because it was a solid, so I'm not going to change it at all. But now my zinc is aqueous, so, or rather my zinc chloride's aqueous, so I need to break this up into zinc ions and 2 chloride ions. Okay? So again, my aqueous compounds here, when I do my net ionic equation, I've broken them up into cation and anion. All right, so first of all, why did we do this, right? Why do we break up our aqueous compounds and we don't break it up if it's not aqueous? Because remember, when we take these ionic compounds and we make a solution with them, they will decompose or, break up into their 2 constituent ions. I don't have copper 2 chloride floating around in this solution. I have copper ions floating around separately from chloride ions. They're no longer bound together when I create this solution here. Okay? And then when we wanted to do our net ionic equation, we went through and we struck things out that were on both sides. So I'm going to get rid of these chloride ions from this side and these chloride ions from this side, right? These things that appear as exact matches on both sides of my chemical equation. And we had a special name for those things that appear on both sides of our chemical equation that we cross out. Spectator ions. And we gave them the name spectator ions because that's exactly what they are. They are watching this chemical reaction go down, but they themselves are not players. They're not contributing to this chemical reaction. So our spectator ions do not contribute to this chemical reaction. Because they're not involved in the chemical reaction at all, they also have no impact on the enthalpy of this reaction. So I don't care about my spectator ions when I'm trying to figure out how much heat is absorbed or released by this chemical reaction. I only care about those species that appear in my net ionic equation. In this case, my zinc solid and my copper 2 ions being converted into copper and zinc ions. Right? So for our solution reactions, our aqueous reactions here, we need to look up our reactants and products, not in our general chemical equation, but in our net ionic equation. All right, so let's go to our constants page to those thermodynamic standards, and we'll look it up for our net ionic equation here. All right, again, we are looking for these compounds here. We need the delta H values of all of our reactants and products. Okay, let's see. What are we talking about? Copper and zinc. Cool. So let's go to C first. We'll go to copper. Okay. As a reminder, the delta H values that we're interested are in that very first column. The other two are other thermodynamic variables we're not going to discuss in this course. And I know everybody's very excited to learn what a delta H and a delta S are, but we'll cover that next semester. All right, so we got two values here that we need. First, from copper solid, that's my product. That has a delta H of 0, a delta H of formation of 0. All right, and what's the other one that I need? So I need a zinc ion. That's going to be under the zinc section. What else can I find here? The copper ion. Okay, cool. So let's note here, we do have copper 2 chloride. Why can't I use this value here? I needed aqueous, right? This is the wrong state of matter. This is the formation enthalpy of the solid form, not the aqueous form. So I need that 64.9, the delta H of formation of that copper ion. And copper in its standard state, just like all elements in their standard state, will have a delta H of 0. So let me just go back and annotate that before I forget these values. 0 and 64.9. Cool. Now we need to do the same thing with zinc. Let me just get rid of this. I'm going to go down to Z now. Cool. Everybody take a minute, see if you can't get those last two values that we need, and then finally tell me the delta H of that single replacement reaction. And again, we only need that first column. Okay, you really need zinc solid, which is its standard state, so that delta H is 0. And we need the zinc 2 ion, negative 153.39. Okay, and when I want the delta H of this reaction, what are we going to chant to ourselves here? What minus what? Products minus reactants. All right, we're going to take the sum of the delta H on the product side multiplied by their stoichiometric coefficient minus the sum of the delta H on our reactant side multiplied by their stoichiometric coefficient. So my delta H for this reaction, look on my product side, that's 0 plus negative 153.39 minus my reactants. All right, I'm going to put both of these in parentheses here so that I don't mess up my order of operations. In particular, it's you can actually get away with it from on the product side, but on the reactant side, you need this negative sign to be distributed inside those parentheses for your order of operations to be correct. Okay, so punch that into my calculator. I get a delta H of this reaction of negative 218.29. All right, my units from that constants page, we can just kind of go back to convince ourselves real quick, are kilojoules per mole. So that's my units here. All right, we got to be careful here because this is a subtraction problem. So in terms of my sig figs, it doesn't matter how many my input have. What matters is the position of that sig fig. And in this case, I'm going to be limited to the 10th place by that 64.9. All right, so my final answer here, rounded to the correct number of sig figs, 218.3 kilojoules per mole. Boom. And what can we say about this single replacement reaction here? Is it exothermic or endothermic? Exothermic. All right, so for these aqueous reactions here, we have to first break this up into its net ionic equation, and then we can do kind of our normal scheme of looking up those values and from our thermodynamic standards and doing our products minus reactants to calculate our delta H. All right. One more type of reaction that is going to be kind of heavily featured here, because again, we covered it quite a bit. All right, are those double displacement reactions. I'll look at a precipitation reaction here. I'm going to go to our constants page. I'm going to grab this. Tell you, we'll just need this bottom half down here. Oh, never mind. Get the whole thing. Okay, so these are another one where we can predict our products. All right, so we're going to mix together silver nitrate and sodium sulfide. And I want everybody to take a second and predict the products of this equation given our constants page here, our solubility table. And then once you have that, you're going to have to use the net ionic equation in order to determine the enthalpy of this reaction. So see if you can't get me a balanced chemical equation using our solubility table to figure out your products. Okay, and then once you have that, you're going to get a net ionic equation. Alright, so I need to swap my cations here. I'm going to pay attention to my charge when I put them together. So sodium nitrate is NaNO3. And then when I do my silver sulfide, silver has a charge of +1 and sulfide has a charge of -2. So my formula is Ag2S. And in order to get my state of matter, I need to look up these compounds on our solubility chart. Both sodium ions and nitrate ions are always soluble. So this gets that AQ designation. And then the silver sulfide, I'm going to look up my cation, my sulfide. I'm going to look up my anion. There it is. So the sulfide ion. This tells me that most sulfide ions compounds are insoluble unless it's paired with one of those group 1 metals or ammonium, and in this case it's not, right? So this compound here would be my precipitate. Okay, so now I need to take this and do my net ionic equation. I need to make more room, sorry. All right, which one of these in my chemical equation am I not going to break up? That's solid, right? Everything else I'm going to break up into its constituent ions. My silver ion. Oh, I lied. I got one more step to do with this chemical equation above. Balance it. All right, trying to move on too quickly. I'm not balanced here. I need 2 silvers on my reactant side. And that means I need 2 sodiums and 2 nitrates on my product side. Cool, and that'll be important for when I do my net ionic equation here because everything needs to remain balanced. My 2 silver ions plus my 2 nitrate ions. Two sodium ions and that 1 sulfide ion. Okay, break up my aqueous product into its 2 sodiums and 2 nitrates. And then my solid product, I'm just going to copy and paste. I'm not going to try to break it up or add charges or anything like that. Okay, and so what are my spectator ions here? My nitrate ion, I know that's a spectator ion because I get to get rid of it. What else? Those sodium ions. So my net ionic equation here are 2 silver ions reacting with 1 sulfide ion to form solid silver sulfide. And this is the equation that I'm going to look up in order to figure out what the delta H of this reaction is. All right, so let's go to our constants page. I need silver. All right, cool. So take a second and grab what you need from this section here. This is going to be all of our silver-containing compounds here, compound or ions. So to be clear, the values that I need is that aqueous silver ion, that 105.79. And I also need that solid silver sulfide, my precipitate, negative 32.6. Okay, in order to get my other compound, I'm going to need to look under sulfur's section on this table here. All right, so everybody take a minute and you can finish off this problem. I need that aqueous sulfide ion, which is 41.8. right, so I need to do my delta H of my reaction is products minus reactants. So I got that negative 32.6 value from my products. I'm going to subtract off my reactant side. And this is where if you forgot to put those reactants in parentheses, you would not get the correct answer here. All right? I'm going to have to do 2 times that 105.79 that I looked up for that silver ion. Why am I multiplying it by 2? Because of my stoichiometric coefficient from my balanced chemical equation. And now I'm going to add on that 41.8 from that sulfide ion. So if I punch this into my calculator here, I get negative 220.76, 0.78. My units based on those thermodynamic standards are kilojoules per mole. All right, and then how many decimal places should I have if I'm being good about my sig figs? Because remember, it's not a counting game. I'm not going to count my number of sig figs in these inputs. I'm going to specifically look at the number of decimal places. And I will be limited to 1 decimal place by that 32.6. Oh, did I jack that up? Oh, shit. Hold on. It's like negative 250 something. I forgot to do negative 36. Cool. All right. Whoops. Oh, that makes sense. Never mind, negative 285.98. Again, kilojoules per mole. All right, and again, if I'm being good with my sig figs here, I'll need 1 decimal place in my final answer. 9.8, wow, struggling today. Oop. Negative 286.0 kilojoules per mole. Okay, so for our aqueous reactions, right, we talked about these net ionic equations where we went through and we canceled out these spectator ions. And that's because these spectator ions, they didn't participate in that chemical reaction at all. So he kind of said, all right, our net ionic equation shows us what's really happening in our chemical reaction. Our silver ions are reacting with sulfide ions to make solid silver sulfide. Okay? So if we want to figure out the delta H of this reaction, again, we don't care about those spectator ions. They're not participating in this chemical reaction. So we're going to first get our net ionic equation, and then we can look up those ions in compounds using that same method we learned how to do last time. Products minus reactants, and we can figure out the delta H of these solution reactions. Okay, so again, we got a few methods for calculating our enthalpy. One is Hess's law. That's that complicated kind of pain in the butt process of taking known reactions and combining it together to get your overall reaction. We have our thermodynamic standards that we can look up. For most reactions, there's nothing special about it. Just look up your reactants and your products, and then it's products minus reactants multiplied by their stoichiometric coefficients. For aqueous reactions, we got a little bit more of an involved process where first we have to get our net ionic equation. All right? And we're going to kind of leave this for next time because we're not going to rush anything in here. We got one more method to calculate enthalpy here, and that is using what's called bond dissociation energy. All right, chemical reactions are all about making and breaking chemical bonds. And your bond dissociation energy is the amount of energy required to break a bond. All right, so in any chemical reaction, you're breaking chemical bonds. All right, but you're also forming new chemical bonds when your product starts to form. And it turns out that the exact same amount of energy is released when those new bonds are formed. All right, so chemical reactions are all about making and breaking bonds. You got to put in energy to break bonds, but then when the new bonds are formed, there will be a release of energy. All right, and so we can use these bond dissociation energies to predict our enthalpy of a reaction by considering what bonds are being broken and what new bonds are being formed. Okay. If you get more energy that's released when new bonds are formed than you had to put in to break bonds, that's an exothermic reaction. There's a net release of energy. If we look at our last example that we did, what is this, an endothermic or an exothermic reaction? Exothermic. All right. In fact, both of these solution reactions that we looked at were exothermic reactions. Okay? This one we actually did in the lab. We know this reaction does occur. We used copper sulfate, but again, that spectator ion isn't doing anything. We've done a single replacement reaction with zinc and copper ions to make solid copper and zinc ions. We know that reaction happens. All right, that's an exothermic reaction. We use our solubility table. We know that this reaction happens here. It turns out that most reactions that occur spontaneously at room temperature are exothermic reactions. The universe likes stuff that releases energy. All right, so you're going to see a lot of your reactions. We can dream up any chemical reaction that may or may not happen, right? But a lot of these reactions that we know do occur turn out to be exothermic reactions, where they release more energy when new bonds are formed than you had to put in to break old bonds. All right, and so that's what we'll go to next time. We'll have one more way for calculating enthalpy, those bond dissociation energies. Cool. Great.